Okay. Stop. Oops. We are still in chapter 3. We'll see, from here. Okay. Where are we? We reached slide number. We finished this one last time, right? We finished slide number 84. Okay. And now we are on slide number 85. Okay, is there any questions you want to ask? Okay, any questions, guys? Okay, hey guys, if there is, if you have something, that you don't understand, let me know, okay? I don't want you to just sit and listen and you don't understand. I want you to understand. Everybody has to understand, okay, guys? Okay, all right. Let's do this example. Okay, all these examples that I give you in this class, okay, they came in one time or another in the exams. Okay, and that's why I'm giving you these examples. Okay, guys. All right. Listen to this example. For the Zener diode circuit shown below in this example, the data sheet of the Zener diode gives the following information. Okay, said VZ is equal to 15 volt. So he, this guy, he drew this circuit. Okay, and he said, the VZ spec, okay, or in the data sheet, VZ is equal to 15 volt. And remember that what I said before, that VZ is always taken at IZT, which is the test current, okay? And then it gives you, he gave us this IZ is equal to 0.25 milliamp, IZT equal to 17 milliamp, IZ max is equal to 100 milliamp, and RZ is equal to 14 ohms. Okay. What he wants us to do, calculate the value of R for maximum Zener current with no load. Okay, so he didn't put any load. He just want to calculate the maximum R, this R here. Okay, so the first thing you have to do, everybody's listening, okay, take this one here out, the Zener diode, and replace it by its equivalent circuit, which contains VZO in series with RZ. Everybody see that? As I can see over here. Okay, now what you have to do, the first thing you have to do is calculate VZO. Okay, and you will say VZ is equal to VZO plus IZ RZ, where IZ, guys, is IZT. Okay, right now, when you want to calculate VZO, okay, calculate VZO when VZ is at 15 volt and IZT at, in this case, 17 volt, okay? All the time, do this, okay? Okay, substitute, and you will see that VZO is equal to 14.762 volt. Okay, once you calculate VZO, you can use it through the whole problem. Okay, it will not change. Okay, VZO will be constant, but you have to find it first. Understood? Everybody get that? Okay, so that's how we calculate VZO in this case. All right, now now we come back to our question. He said calculate the value of R for maximum Zener current with no load. Okay, now for maximum Zener current, that means the Zener current, the maximum Zener current will flow through the diode means over here. And once it flows, the thing that's going to change is the voltage across RZ. VZO will not change. VZO is constant. You already calculated it. Everybody got that? So the thing that's going to change is the voltage drop across the RZ. Everybody got that? All right. So what is the maximum here? The maximum Zener current is given by 100 milliamp. Okay. So go ahead and calculate what is VZ now when the current flowing at max. Of course, you know, VZ will vary a little bit. Okay, will vary, will become more or less, okay, than something like VZ. Okay, calculate VZ and use VZ is equal to VZO plus IZ, in this case max. Okay, because you know he wants us to calculate the max, the value of R. Okay, so substitute for IZ is equal to 100 milliamp, and you will find that VZ is equal to 16.62 volt. Everybody get that? All right. Now, 16.162 volt will be over here, right, at this node here, okay, which is across the diode. Okay, now to find the value of the resistor, remember that IZ will be equal to IZT, right? Because you know I don't have any current flowing over here because I didn't connect any resistor at the output. Okay. Okay, so using KVL or use is equal to what? Is equal to what? R is equal to VI minus VZ over IZ max, okay, which is equal to 24 minus 16.162 divided by 100 milliamp. That will give you 78.4 ohms. So R will be 78.4 ohms. Okay, any questions? All right. Now the second question, he said calculate the maximum output power. Remember the power, we dealt with it when we took Eeng to 100 or 200 and said power is equal to VI. Okay, okay, and calculated when IZ, of course, at minimum. And he said use R in that part, in the face part, which is part A in this example. Okay. Therefore, you know, we have to calculate VZ when IZ is at min. What is the minimum? The minimum is called IZK in this case. That's the minimum. Okay. And it is equal to, in this case, 0.25 milliamp. Calculate VZ. Okay, substitute for VZO. VZO doesn't change. Same thing, 14.762 volt. Put it there and put the value of R and multiply it by IZ min, which is in this case IZK, which is equal to 0.25 milliamp. And that will give you VZ 14.766 volt. Okay, so when the IZK is equal to, or the IZ min equal to 0.25, VZ is not 15, no, it will be less. Okay, will be equal to 14.766 volts. Okay, all right, now we can calculate IT, right? IT over here. How? Is using what, KVL. VI minus 14.766 divided by the R, okay, over here, which is 78.4, and that will give you 0.1178 amps, okay, give you IT 0.1178 amps, okay. Okay, now to calculate the power, which means that you have to put a resistor here. Okay, there will be a load over here, and the load will take a current, of course, right? A current. Do you know what the current is? You didn't know what the current is, okay? But there will be a load, okay? How we're going to find this current is applying KCL at this node. IT is equal to IL, which is the load current, plus IZ, where IZ in this case, you got it what? IZ min, right? Okay. Calculate IL, and IL will be equal to 0.1175 amps. Okay. Hey, you guys notice when IZ is min, okay, when IZ is min, IL will be max. Everybody get that? And vice versa. When IL is max, okay, IZ is min. And when IL is min, IZ will be max. Everybody get that? Okay, that's the rule. Okay, now we found IL. Okay, now the power is equal to VZIL. Okay, remember this is the maximum output power. Okay, the output at the output over here. Therefore, power is equal to VZIL, and that will give you 1.735 watt. Okay. Any questions? Questions? All right. Okay. This is an interesting question and easy to. It said here, the Zener diode in this circuit here, okay, it's used as a regulator, of course, right? Right? Okay. He said, giving the parameter for the Zener diode, RZ is equal to 7, which means that it's very, very, very good Zener diode. Okay. The less RZ for the Zener diode, the better. Okay. Okay. And IZ max is 70 milliamp. IZK, which is the minimum, is 1 milliamp. And he said VZ is equal to 5.1 volt. Okay. At IZ equal to 449 milliamp. Okay. This is from another book, this example, okay, which means that IZ means IZT, okay, got it? The book, some other book, they expect you to know that, okay, they expect you to know that. Means, VZ is taken 5.1 volt at IZT, of course, it's equal to 4.49 milliamp. Okay, so the first thing is we're going to calculate VZO. Okay, as in this example, okay, he said find VZO. Okay, find VZO, and we know how to find VZO. We said VZ is equal to VZO plus IZRZ, where IZ in this case is IZT. Substitute, and you'll find VZO is equal to 4.757 volt. Okay, and that's constant, it will not change. Okay, everybody get that? It will not change. So VZO will not change, it will stay like this, okay, through the whole problem. Okay, now, question number two, he said, draw the circuit after replacing the Zener diode by its model, okay, by its model. Draw the circuit. I will redraw the circuit. Okay, so we redraw the circuit on slide number 87, and the circuit will become like this. Okay, so this is VZO, and this is here RZ. Remember, RZ is equal to 7 ohms, and VZO is equal to 4.757, right? Okay. I made it, 4.8. So why? Because I didn't have space to write the whole thing. Okay, now over here I have RL, okay, and IL will flow through RL, and over here I have IZ will flow through the Zener diode, okay, and over here is IT, okay. All right, now what does he want us to do? He wants us to determine the minimum and the maximum permissible load resistor. What is the minimum permissible resistor that you can place over here with the R is equal to 22 ohms? Okay. All right. Okay, now let's find the minimum resistor RL that you can place here. What is the minimum? Okay, here's what I'm going to say. When the RL is minimum, everybody's listening? When RL is minimum, IL will be maximum. Everybody get that? When RL is minimum, IL will be maximum. And when IL is maximum, IZ will be minimum. Everybody get that? Okay. All right. When RL is max, IL will be min. Okay. When IL is min, IZ will be max. Everybody get that? Okay. All right. Now let's calculate RL at minimum. When RL is minimum, IL is maximum, IL max, and IZ is minimum. Okay, therefore, let's calculate VZ. We know that VZ is equal to VZO plus IZ multiplied by RZ, where IZ in this case is minimum, which is, he gave us minimum IZK, which is 1 milliamp. So substitute, and VZ will be equal to 4.764 volt. Okay, 4.764 volt. Okay, all right. Now, how am I going to calculate IT? Well, I use KVL, of course, in the phase machine. I use KVL, and I know that this one here is what, 4.76. Okay, and this is 8. So IT, the current flowing here is 8 minus 4.764 divided by 22, and that will give you 0.1471 amps. Okay, can I calculate IL at max? Yes, I can, right? Because I apply KCL over here. KCL, IL is equal to IT minus IZ. Okay, I have IT and I have IZ. I can calculate IL max. IL max is equal to 0.1471 amp minus 1.1 amp over here. Sorry, 1 milliamp. And that will give you is the same 0.1461. Okay, amp. All right. And now to find RL, I use Ohm's law is equal to VZ over IL max. And I already calculated the VZ, which is 4.764 divided by IL max, and that will give you 32.61 ohms. Okay. Any questions? All right. So we calculated RL min. Okay, RL min. Okay, now we're going to calculate RL max. What's RL max? RL max is taken when IL is min. Okay, when IL is min, RL will be max. And when RL is max, IL is min, and IZ will be max. IZ will be max. Okay. Find out, what is the VZ. VZ is equal to VZO plus IZ max multiplied by RZ, and that will give you 5.247 volt. Okay, 5.247 volt. Find IZ, find the IT, and that will give you 8 minus this voltage, 5.247, divided by 22 will give you 0.12513 amps. Okay, this is IT total. I use KCL to find IL min. IL min will be equal to IT minus IZ max. Okay, substitute, and that will give you 0.05513 amps. Okay, find RL using Ohm's law, which is VZ, which is 5.247 divided by IL min. Okay, and that will give you 95.16 ohms. Okay, any questions? No questions? Okay. At all? Okay. Slide number 89. Okay, this is another example here. Said for the Zener circuit shown below, okay, the data sheet or the spec sheet of the Zener diode gives the following information. VZ 15 volt at IZT, IZK is equal to 0.25 milliamp, IZT is equal to 17, IZ max is equal to 100, and RZ is equal to 14. It's the same spec as we seen in the example number 1 at the first example, right? Okay, what does he want us to do? He said calculate the value of R for maximum Zener current with no load. This one here we already did, and the example we just finished. I mean not we just finished, but before example number 1. Okay, and then calculate the maximum and minimum value of RL. Okay, and he said use R in part A, and we saw how we calculated in the first example. We calculate VZO, substitute, and that will give you 14.76. And then for VZ max, find VZ for maximum Zener current, maximum, and VZ will be equal to 16.162 volt. And then find R here, and then R will be 78.4 ohms. We have seen that before, right? Okay. Now we want to calculate the maximum and minimum value of RL. Okay. Okay. So for maximum load resistant RL, we apply KVL over here. We apply KVL to find I, which is over here. Sorry. Okay, and that will give us what? 24 minus 16.16, which is this one here, okay, divided by 78.4, and that will give you I is equal to 100 milliamp over here. Okay. Now, what we're going to do is that we're going to calculate IL. So we're going to calculate IL. IL is equal to what? Is equal to I minus I max. Okay, and that will give you 100 minus 100 will give you 0. So IL will be 0. What does that mean? If we want to calculate RL, we divided VZ by IL, which is 0, and that will give you infinity. That means it's open circuit. Open circuit. Actually, this is, the first question in reverse. Remember the first question that we solved before, which is what is it? This one here. Okay, remember, same, and reverse. Okay, all right. So it's an open circuit. Okay, now how are we going to calculate the minimum RL min? Remember that RL min, okay, when IL is max, okay, and IZ will be min, okay. So let's do that, okay. For minimum load resistor RL min, we find VZ min, and VZ min is 14.766 volt, okay. All right, guys. Okay. KVL, that will give you point for I, because we want to calculate I. I will be equal to 0.1178 amps. Apply KCL over here to find IL max, and IL max will be equal to 0.1175 amps. Okay. All right, use Ohm's law. Divide VZ min, which is 14.766 divided by this current IL max, and that will give you 125.5 ohm. So this is your RL min. Okay. Any questions? Any questions? Okay, no questions at all? Okay. All right. Now, is there any question before we have this example? Any questions, guys? Okay. 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 This is from another, I think, yeah, from the same book, right? Because, you know, the data sheet is the same. So this one here is the same as before. So the data sheet of the Zener diode shown below gives the following information: 15 volt for VZ at IZK. IZK is 0.25 milliamp. IZT is 17 milliamp. IZ max is 100 milliamp, and RZ equal to 14 ohms. Calculate the maximum value of R for no load. Okay, that means RL is removed. Okay, and this here, you know, and this one here, maximum, but actually, you know, he's supposed to say minimum, so he made a mistake here. I mean, there's a mistake here, but nevertheless, we'll just calculate it at what's written here. Should be minimum, not maximum. Okay, all right. So the first thing is we're going to calculate VZO, okay, for the minimum, because he's asking about maximum value. So we use minimum, okay? And for this case, the minimum is, we calculate VZO when IZT is equal to 17. So we calculated VZO, which is the same thing as we did before in the other two examples. Okay, and now we want to find the maximum value. If we want to find the maximum value of R, okay, that means, you know, this value over here, the value drop across the Zener should be minimum to give us, you know, big value over here. Okay, so we found VZ for the minimum Zener current, and VZ is equal to VZO plus IZ min RZ, and that will give you 14.66 volt. Okay, find R max is equal to VI minus VZ divided by I Z min, and that will give you 36.938 K. K ohm. Okay, now he's supposed to actually, you know, he said minimum, not maximum, but nevertheless, we are going with what he did. Okay. All right. The second question here, he said, if RL is 1K, okay, if RL is 1K, then calculate the variation in V out if VI varies between plus or minus 10%. Use R and A. Okay. All right. So here we go. When the voltage here is plus 10%, It means that's the voltage over here will become 26, okay, 0.4 volt, okay. 10% of 24 is 2.4, okay, add it to 24, and that will give you 26 volt here. Okay, that's 10. That means your 10, your VCC went up 26.4. Okay, we have two meshes here. We apply mesh analysis. Okay, take KVL and mesh 1. How are we going to do that? Okay, minus 26.4 plus I1 multiplied by R plus VZO. VZO doesn't change. Plus, everybody is listening, plus RZ. Okay, bracket I1 minus I2 bracket, okay, is equal to 0. Why did we say that? It's because according to what we took in Eeng261, okay, when you are in mesh 1, then you start with like this, RZ, okay, bracket I1 minus I2. Okay, don't forget that. All right, solve and you'll get this equation number 1. Okay, go to mesh number 2 and do the same. Okay, I2 RL plus, okay, plus what? Plus 14, which is the RZ, multiplied by I2 minus I1, bracket minus VZO is equal to 0, and solve, and you will get this equation number 2. So you have two equations, two unknown. Okay, hey you guys, when you do something like this, this one here, that the variable here I1 should be at the beginning here, and I2 second. The second equation, the same thing, I1 here first, and then I2 second. Okay. Now the equation are ready to be processed. How are you going to do that? Is use your calculator. Okay, use your calculator to solve this. Your calculator will split I1 equal to 0.3205 amp, and I2 is equal to 0.0145, okay, amps. Okay, our concern is we need to find the I2. We find I2, we multiply I2 by RL to find V out. Okay, we want to find the variation here. And V out will be equal to 14.56. Okay, got it? 14.56. Okay, now, what we're going to do, we're going to reduce the voltage by 2.4 volt. Okay, this is on slide number 94. Okay, and therefore, VI will be equal to 21.6. Okay, 21.6. Do the same thing, KVL. And you'll find that when you do that in mesh 1, you will get with this equation here. And do the same thing for mesh 2, and you will get this equation. Use your calculator to solve these two equations, and your calculator will split this number I1 0.195057 amps, and I2 is 0.0145605 amps. Therefore, calculate V out is equal to I2 RL, and that will give you 14.561, okay, volt. See this one here? I mean, the voltage varies by what? By 10% from 26, okay, 26.4 to 21.6. It varies. This one varies, right? But your output is held at 14.56. See it? That hardly changes anything. Okay, your output didn't change almost. Okay, so that's why Zener diode is good. Is being used as a regulator. Okay, this one here is in your. What is this one? Yeah, this is in your another your reference book. I think this is from your reference book, I believe. Yeah. No, this is from your Sidran Smith book. This is from your Sidran Smith book. Okay, this example here. I said here the 6.8 volt Zener diode in the circuit shown below, which is this one here. Okay, is specified to have VZ equal to 6.8, and it's taken at IZT 5 milliamp. Hey, you guys, see what I said before? Is when they said VZ at IZ, they mean at IZT. Okay, so IZT in this case equal to 5 milliamp. RZ is equal to 20 ohms. That's a big one. Okay, and IZK, which is the minimum, is 0.2 milliamp. Did he give us IZ max? He didn't give us IZ max. Neither doesn't matter. Okay, he said the supply voltage, which is VCC, is nominally at 10 volt, but it can vary by plus or minus. Okay, 1 volt. Okay, so this is the circuit here. This is the same circuit as we have seen before, except it's drawn differently, but it's the same circuit. Okay, it's the same circuit. Okay, so what does he want us to do? He said find V out with no load, okay, and with V plus at nominal value, which means nominal value means V, this is VCC, nominal value means 10, okay, 10 volt, okay? All right, so what we're going to do is, first of all, when we are giving a problem like this, the first thing is we're going to take this one here, the Zener diode, replace it by its model. The model is over here. Okay, this is the model. And the initial thing, what he said no load. Okay, no load. What is the no load? That means there's no RL. Okay, which means that I will flow like this all the way down. Okay. All right. So the first thing is we're going to calculate VZO, just like what we did before. Okay. And VZO, how are we going to calculate? We said VZ is equal to VZO plus IZT RZ, and substitute for IZT is equal to 5, and solve for VZO, and VZO is equal to 6.7 volt. So this 6.7 volt will not change through the whole problem. Okay. Any questions? Any questions? Okay. Now, having found, VZO, we can calculate the current I, which is equal to IZ, right? We just use KVL, right? Use KVL from here down to here, minus VCC plus I multiplied by R plus VZO plus I multiplied by RZ. Remember, this is I and IZ are equal. They are the same, right? Solve for IZ or I, okay? And that will give you I will be equal to 6.35 milliamp. Okay, that's the current flowing through the Zener diode when VCC is equal to 10 volt. Okay. Now what we're going to do is we're going to calculate VZ, which is at the output. Okay, and VZ would be equal to VZO plus IZ RZ, where IZ is the one that we just calculated it here, which is 6.3 milliamp, 6.35 milliamp. Substitute, and you will find that VZ, which is equal to VZO, okay, is equal to 6.83 volt. Okay, 6.83 volt. Everybody got that? Any questions? Any questions, guys? Okay, very good. Very good.
VC and V output are the same because they are parallel, or
No, this is here. Between here over to here is VZO, right? Sorry, VZ, right?
uh,
Okay, and between here and the ground also be out, right? There is no load right now. Okay, so this one and this one are the same. Basically the same, right?
uh,
Okay, all right. Shall I draw it? Maybe I should. This is better. Okay, so this one here. Okay, between here, from here, okay, from here to ground, to here, is called VZ. And that's why, we said VZ is equal to VZO plus IZRZ, right? Okay, and since VZ over here and V out is over here, of course, right? So VZ is the same as VZO. Okay, any questions? All right. Now what we're going to do, we're going to calculate. He said, find the change in V out, okay, resulting from the plus or minus 1 volt change in VCC. Okay, hey you guys, some of the book they don't write VCC, they write V plus. Okay, they write V plus, which means VCC. Okay, find the change. Okay, when the VCC plus or minus 1, and he said, remember that delta V out divided by delta VCC, and usually expressed in millivolt per volt, and it is known as line regulation. Okay, so line regulation is equal to delta V out over delta VCC. Okay, that's what he wants us to do. This is the B type. All right. So what we're going to do is we said, okay, remember that this one here is constant. Okay, this one here is constant. Okay, so what affect the VZ or VZO in this case? What affect, okay, is the voltage across RZ. Okay, RZ. So in this case, what we're going to do is that, you know what, forget about VZO, we just remove it. We know that it is constant. We need to find just the delta, okay? So what we're going to do, we come here, we draw the circuit again. So this is V plus over here, this is the R, okay, and this is V out, and this is the RZ. We remove the VZ for a moment, just ignore it because it's constant, okay? And therefore, if you want to find V out, we take VDR, right? The VDR is equal to delta V out is equal to delta VCC multiplied by RZ divided by the sum. Everybody get that? Okay. All right. And that's what, and that's what the book is doing. This is it, right? Yeah. So delta V out is equal to delta VCC multiplied by RZ divided by the R plus RZ. He just took VDR, okay? All right, substitute plus or minus, okay? This is the delta here, and it will give you plus or minus 38.5 millivolt. This is the delta V out. Okay, now if you divide the delta V out by delta VCC, is the same thing, and we call that, line regulation. They call it line regulation, 38.5 millivolt per volt. Okay, so that's what the line regulation means. Okay. All right. The third one here. The third one, he said, find the change in V out. Okay, find the change in V out resulting from connecting a load resistor RL that draws a current IL equal to 1 milliamp. Okay, and hence find the load regulation. Okay, load regulation means delta V out over delta IL. Okay, over delta IL, that's in millivolt per milliamp, expressed in millivolt per milliamp. Okay, so delta V out over delta IL is called load regulation. Okay, all right. Remember that, you know, when we have the circuit here, okay, we connect RL to it. Okay. Now what happens is that we have a current flow here called IL. And in our example, he said, you know, IL will be equal to, it will draw 1 milliamp, okay, from the current that's flowing over here. So when it draws 1 milliamp, that means IZ will be reduced by 1 milliamp. Everybody get that? IZ will be reduced by 1 milliamp. Okay? We have seen that before. I said remember that's when RL, for example, didn't I say that before? When RL is min, IL will be max, and therefore IZ will be min, and vice versa. In this case, in this example, he didn't say that. He said that RL, some value that will draw RIL equal to 1 milliamp, which means that when this guy draw 1 milliamp, IZ should be reduced by 1 milliamp. Okay, got it, guys? All right. So there you go. IL equal to 1 milliamp. Okay, that means the current that goes through the Zener diode will be reduced or decreased by 1 milliamp. Okay, use the Ohm's law here. Delta V out is equal to RZ multiplied by IZ. Okay, which is in this case, okay, use Ohm's law. Okay, RZ is 20 multiplied by minus 1, because, you know, it's decreased by 1 milliamp. This is IZ, it decreased by 1 milliamp. And that will give you minus 20 millivolt. Okay, minus 20 millivolt. Okay, which means that, you know, delta V out divided by delta IL, in this case, IL is 1, okay, 1 amp, and that will give you what? Still minus 20 millivolt per milliamp. Okay, any questions? Any questions? Okay, now question D, E, and F are the same. Just go over them, go home, and the same thing, you know, do the same thing. Okay, we'll leave them for you to go over them. All right, slide number 99. Okay, we come to a point where, you know, this is a summary, okay, for what we already taken. Especially we start with half-wave rectifier. So this is half-wave rectifier, okay? And for example, this is SI. That means, you know, the peak value of the output will be what? Will be V input over here, Vs, minus 0.7 volt. And that will give you the V out. The average value of the output, V out. Okay, if we go to the sketch, this is a sketch of the output. Remember, this is a sketch of the half-wave rectifier. Okay, the average value, or the VDC, sometimes we call it, is equal to VP or Vmax divided by pi, or equal to 0.318 multiplied by V max over here, the output max. Okay, and The diode, okay, we'll see the full VS, and that will give you what PIV is equal to P out secondary, the P out secondary, okay? All right, we'll give you the P out secondary, okay? All right, any questions? Any questions? All right. Okay, center tab, we don't take center tab, we haven't taken it, okay? But we took a bridge full rectifier, okay? Bridge rectifier. Okay, now if we want to find the peak value of the output, V out is equal to what? Is equal to V secondary, okay, minus 2 diode drops, which is in this case 1.4, and that will give you the output here. Okay, if we're going to draw it, we draw this or sketch it. We sketch it like this. This is the output of the full rectifier. Okay, hey, you guys, don't confuse the half wave rectifier with full wave rectifier. Okay, remember that the half wave rectifier, one of these will be missing. Okay, and full rectifiers, the output will be unipolar like this. If you want to calculate the V average will be equal to what? 2 V out divided by pi, or equal to 0.636 V out. Okay, and the PIV will be equal to what? Will be equal to V out plus 0.7 or VS minus 0.7. VS over here, it's secondary, okay? Remember, this is secondary. Over here, we have primary, okay? Any questions? Okay, and this one here is a summary for ideal VDC. This is the commercial here, okay? And you can see for halfway rectifier bridge, we don't take center tab, okay? Diode limiters, we are not going to take diode limiters, so, okay. But we're going to take what, we're going to take special diodes, okay, special diode, okay, special diode. Okay, well, the first one, we call this as, what we call it what? Schottky diode. And Schottky diode, the symbol for it is this, okay? And this is the cathode, and this is the anode. And there's a scientist, a German scientist, who lived in 1886 to 1976, okay? And his name is Walter Hans Schottky. That's why, you know, they named this diode after his name, Schottky, okay? And he's the one who pioneering and developing of the Schottky diode, okay? And what is the Schottky diode, okay? Or sometimes they call it Schottky barrier diode or SBD, okay? How do they make it? Is they take, say, for example, N type, okay, and they take metal. They throw away P type, okay. So they take N type and connect it to a metal, okay. And by doing this, they got rid of the minority carriers, or there are no minority carriers, okay. For example, the holes, there are no holes, okay? Like the normal diode has N type and P type, where P type has holes. Okay, so they got rid of the P type, and they connect just metal. Okay, and by doing this, the majority carriers are what? Electrons. Okay, electrons. Okay, and because because there are no minority carriers, the diode, which is the the Schottky diode, is really fast, very, very fast compared to the normal diode. Okay, and that's why if you have a fast circuit, use Schottky diode. Okay, instead of the PN diode. Okay. Also, because of we got rid of the minority carriers, the forward voltage drop across the diode is lower than the p-n junction diode, normal p-n junction diode. So it dropped from 0.6 volt to 2.8 volt, which we call it 0.7 volt, to about 0.3 to 0.4 to 0.5. It's about 0.4 volt. So it dropped from 0.7 volt to around 0.4 volt. Okay, that's the another advantage of it. Okay, guys. The another diode in this case here called varactor diode, or better known as varicap diode, or varactor diode, or variable capacitor diode, okay, or variable reactance diode, or tuning diode. Okay, all right. And what happens that this diode, okay, has a variable capacitance that is a function of the voltage impressed on its terminal. Okay, it uses actually the charge stored in its depletion layer when it is reverse bias. So this one here, when it is reverse bias, it uses that, and it uses the depletion region here, okay, as a variable capacitor. And we use it where? We use it in so many things, okay? For example, they call it parametric amplifiers. We use it in phase lock loops. We use it in oscillator. We use it in television. We use it in radars, okay? And also all good things, okay, for this diode, okay? The third one, okay, we call this photodiode, okay, and it's a type of photo detector, okay, capable of converting lights into either current or voltage, depending upon the mode of operation, okay. We use this for in solar power. So it converts lights into either current or voltage. Okay, so the symbol for it is this, with two arrows coming from as a beam of light. Okay, and we use this in what? In solar. We use it also in fiber optic, okay, transmission, or in optical storage, or in CD-RAM. Okay. Another type, which is we're familiar with it, okay, is called light emitting diodes, or LEDs. Okay, LEDs. Okay, a light emitting diode, LED, is a semiconductor light source. Okay, and LED are used as indicator in many devices. As you can see, all the devices that you can, almost all, okay, for instrumentation, for example, they use LED now. Okay, all right. So when a light emitting diode is forward bias, okay, that means switched on. Okay, Then electrons are able to recombine with the electrons holes, okay? And therefore, it will release energy in the form of photons, okay? They call it electroluminescence, and the color of the light that is emitting from the diode correspond to the energy of the photon, which is determined by the energy gap of the semiconductor. Okay, and this is the symbol for it. Okay, with the two arrows up. And over here this is the physical, okay, that you will see, okay. And as I said before, how do you know that the anode from the cathode? The anode usually longer than the cathode. Okay, but if somebody came and cut the leads equally, what will happen? There is another way to recognize the cathode from the anode. There is a flat. Can you see this one here? Flat spot here. That flat corresponds to the cathode. Okay. Everybody got that? Any questions? Okay. So with this, we finish this chapter 3, and we'll be in chapter 4. Okay, we'll be in chapter 4. Any questions? Any questions? Any questions, guys? Any questions in chapter 4? Okay. No questions? All right. If there is no questions, okay, I will let you go. Okay, so let me stop recording.